Good morning, class. Here's chapter 3, functions, section 3.4, composition of functions. So we've covered sections 3.1 to 3.3, functions, function notation, domain and range, rates of change and behavioral graphs, and now composition of functions. The objectives are combine functions using algebraic operations, create a new function by composition of functions, evaluate composite functions, find the domain of a composite function, decompose a composite function into its component functions. Let's quickly remind everybody, dependent and independent variable, function and function notation. First, here's the DQ, difference quotient, f of x plus h minus f of x over h, which is rise over run. Dependent and independent variables for an equation in variables x and y. If the value of y depends on the value of x, then y is the dependent variable and x is the independent variable. Relation, a set of ordered pairs. Domain, the set of all input or x value or independent variables. Range, the set of all output values, y values, dependent variable for a relation. And as far as a graph is concerned, if you could lay it down along the x-axis, the portion it covers is the domain. Along the y-axis, the portion it covers is the range. A function is a relation in which each element in the domain corresponds to exactly one element in the range. A vertical line test, or short VLT, if a vertical line can be drawn so that it intersects a graph at more than one point, then the graph does not represent the function. If a vertical line cannot be drawn so that it intersects a graph at more than one point, then the graph represents a function. A function is one-to-one if each element in the range corresponds to exactly one element in the domain. And then we have horizontal line test, or HLT, if a horizontal line can be drawn so that it intersects the graph of a function at more than one point, the graph is not a one-to-one function. So this is the synopsis of what we've learned. And in short, function, the x coordinate cannot repeat a one-to-one function. Now, not only the x, also the y coordinates cannot repeat. So the average rate of change of y with respect to x is f of b minus f of a over b minus a. Basically, if you have 2 points, connect them. This is the good old slope, m equals delta y over delta x, and there are various ways of writing them, such as f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1, f of x minus f of a over x minus a, f of a plus h minus f of a over h. Even function, by definition, f of minus x equals f of x makes it symmetric with respect to the y-axis. Odd function, f of minus x is minus f of x, so it makes it symmetric with respect to the origin. For an even function, for every point x comma y on the graph, the point minus x comma y is also on the graph. For an odd function, for every point x, y on the graph, the point minus x and minus y is also on the graph. A function is increasing on an open interval I if for any choice of x sub 1 and x sub 2 in the interval of I, x sub 1 is less than x sub 2, we have f of x sub 1 less than f of x sub 2. A function is decreasing on an open interval I if for any choice of x sub 1 and x sub 2 in the interval of I with x sub 1 less than x sub 2, we have f of x sub 1 larger than f of x sub 2. And a function f is constant on an interval I if for all choices of x in I, the value of f of x are equal. The short version of increasing, decreasing is that basically in the case of increasing, when x gets larger, so does y. In the case of a decreasing, when x gets larger, y gets smaller. That's as simple as it gets. Let's look at formal definition of extrema. Maxima or maximum or minimum points on a curve. Local or relative extreme value. Extrema is the plural of the Latin extremum. A local minimum is the minimum value within some open interval. Local minimum occurs at a point C in an open interval of A to B in the domain if f of C is less than or equal to f of x for all x values in the open interval. So basically, we talk about peaks and valleys, okay? The valleys represent the minimum, the peaks represent the maximum. In an interior part of the graph, a local maximum is the maximum value within some open interval. Local maximum occurs at a point C in an open interval of A to B in the domain if f of C is larger than or equal to f of x for all x values in the open interval. So local mean, local max, local mean, local max. Absolute, also known as global extreme value of extrema, or either maximum or minimum points on a graph. Absolute minimum occurs at the point C if f of C is less than or equal to f of x for all x values in the domain. This is not only a local mean, also an absolute mean. So local mean, local max. This is absolute and local. Local because it's the interior, absolute because there's no other value having a larger, smaller y coordinate. Absolute maximum occurs at the point C if f of C is larger than or equal to f of x for all x values in the domain. So when we look at this graph, local max, local mean, local max. This local max happened to be an absolute max because no other point has a larger y coordinate. So when we refer to extrema, we mean the y coordinates. Needless to say, they may be interested in the location, which you report as either x or x comma y. All right. Now 3.4, composition of functions. Operational functions. If f of x represents one function, g of x represents a second function, and x is in the domain of both functions, then the following operations on functions may be performed. Sum of functions, f plus g of x is f of x plus g of x. Difference functions, f minus g of x is f of x minus g of x. Product of functions, f g of x is f of x times g of x. Quotient of functions, f over g of x is f of x over g of x. As always, the denominator cannot be 0, therefore g of x cannot be 0. So here's a synopsis of that. Let's start with some examples. Example 1, given f of x equals 3x plus 1 and g of x is 5x plus 2, find the following. Let's start with f plus g, which simply put means f of x plus g of x. Let's write both functions. We combine these two into 8x and these two into 3. So the final answer is 8x plus 3. Part B, we are interested in f of x minus g of x. So we write f of x, which is 3x plus 1, minus the parentheses 5x plus 2. So we are going to write this as 3x plus 1 and then distribute the negative sign to get minus 5x minus 2. We can add these two to get negative 2x. We can add these two to get negative 1. So the final answer is negative 2x minus 1. F minus g of negative 2, basically in part B, since we already have f minus g of x, plug in negative 2. If we don't have it, becomes f of minus 2 minus g of minus 2. So we are using this. So we get 4 minus 1 equals 3. We're going to continue with example 2. If f of x is x squared plus x minus 6, and g of x is x minus 3, let's start with f plus g of x, which is simply f of x plus g of x. So let's add these two functions. Because there is a plus sign in between, you don't have to distribute anything. So x squared remains, x and x result in 2x. The numbers add up to negative 9. So x squared plus 2x minus 9. All right. We want f minus g of x which is f of x minus g of x. So now we are going to distribute the negative sign, and we are going to write the first parenthesis unchanged, x squared plus x minus 6. The second one changes to minus x plus 3. So we are going to combine like terms. So x squared remains, x and negative x cancel each other, and the two numbers add up to negative 3. So the result is x squared minus 3. G minus f of x. There are two ways to approach this class. One is to develop it as g of x minus f of x. I'm going to go through that, and then I quickly show you the easy way out, this second method. So we are going to plug in both into a parenthesis, x minus 3 minus f of x, which is x squared plus x. We are going to distribute the negative sign. So the first one, x minus 3, doesn't change. The second parenthesis changes to minus x squared minus x plus 6. And so we want to put this in descending order. So we're going to put this one first. These two cancel each other. Number negative 3, positive 3, a positive 6, they give us positive 3. Since we had this part, everybody, because we had this, all you had to do from here, write the negative of the result, and that would be just as good. Again, since we worked this one out, G minus F is the opposite of F minus G. Example 3, given 2x, given f of x equals 2x plus 7, and g of x is x minus 4, find f of g, which is f of x times g of x. So 2x plus 7 times x minus 4, and you do the foiling. 2x and x is 2x squared, times minus 4 is minus 8x, plus 7x minus 28. And all you have to do, combine the middle terms into minus x. Everything else remains the same. The final answer is 2x squared minus x minus 28. F of x is 16x cubed minus 12x squared plus 8x, and g of x is 4x. Find f over g. By definition is simply f of x over g of x. So we have a fraction bar. This function is at top. This function is at the bottom. Because the denominator contains one term, let's cut it into 3 fractions. This is one, this is the second one, this is the third. So we make up 3 fractions because the denominator has only one term. This is 4x squared minus 3x plus 2. Simple. Use the graph to find the value of the following f minus g of 0, and understand the f function is the blue one, the g function is the red one, and by definition, f minus g means what? F of 0 minus g of 0. So all we have to do, locate f of 0, which means x is 0, find y, which means the y-intercept for the blue function, which is 2. G of 0 is the y-intercept for the red function. So 2 minus 1. So 2 minus 1 equals 1. F of 0 minus G of 0. Pretty straightforward, everybody. We're going to continue with the same graph. The f is the blue one, the g is the red one, and we want g plus f of minus 3. By definition, it's g of negative 3 plus f of negative 3. So you locate negative 3 along the x-axis, everybody. G is the red one, so g of negative 3 is here. which has a y coordinate of 4. Remember, G represents the y coordinate. And f of -3 is here, which has a y coordinate of -1. We add the 2. So we add 4 to -1. The result is 3. G f of 2, G times f of 2. That means G of 2 times f of 2. So now along the x-axis, we are going to locate number 2. For the G function, red function, we are here, which has a y coordinate -1. For the f function, we are here, which has y coordinate equals 4. We multiply the two numbers and we get -4. So that's how you read it from the graph. In general form, the sum, difference, product, and quotient of two functions f and g. Here's the synopsis of how you do that. Example 6, for the function f of x equals 2x squared plus 3 and g of x equals 4x cubed plus 1, find the following. F plus g, by definition, is f of x plus g of x. We've seen it many times by now, so add these two. And as you can see, we like to put this in descending order. So this comes first, this comes second, 3 and 1, they add up to 4. So let me, these two can combine. F of x minus g of x, we write both functions. We are going to distribute the negative sign and write minus 4x cubed, which we are going to write as the first term because we are going with the descending order, minus 1. So we have minus 4x squared plus 2x squared. We combine these two numbers into plus 2. Fg, that means f of x times g of x. Let's multiply these two by foiling. First, we multiply these two, we get 8x to the power of 5. If we multiply these two, we get 2x squared. We multiply these two, 12x cubed. Finally, plus 3. Of course, this is not in descending order. I just wanted to show the foiling. If we want to put it in descending order, we have to interchange these two, okay? So this comes here, this goes over there. F over g, simply f of x in the numerator, g of x in the denominator. That's all, and they can't be simplified. Needless to say, any fractional format, any rational function, if there is a common factor between the top and the bottom, you must find it and get rid of it. Example 7, given f of x equals 1 over x plus 2 and g of x is x over x minus 1, we are repeating the previous example with different functions. So first, f of x plus g of x is just adding the two rational functions. Notice, to add any two fractions, we need LCD, the least common denominator, which is the product of x plus 2 and x minus 1. So if x plus 2 times x, so let me write that. LCD is the product of x plus 2 and x minus 1. So this fraction has to be raised by a factor of x minus 1. So you put x plus 2 times x minus 1 here. This one is 1 times x minus 1. This one is x times x plus 2. You can use one big fraction bar, put them at the top, the sum of x minus 1 and x times x plus 2, or just do it this way. One more time. This one, I'm multiplying by x minus 1. So I'm going to multiply 1 by x minus 1. This one, denominator, I'm multiplying by x plus 2. So I'm going to multiply x by x plus 2. So since there is a sum, all I have to do is just find out what is this product and put them together. So let's do that. This gives us, let me write it here, x squared, there is a plus, okay, and 2x. So to add everything and putting the numerator in descending order, we have x squared, 2x, and x, 3x minus 1, and the denominator, you keep it as a product of x plus 2 and x minus 1. By the way, you can always try to put it in lowest term by factoring. The numerator cannot be factored because if you calculate the b squared minus 4ac, so this is a, this is b, this is c. So let me just write for the numerator. A is 1, b is 3, c is negative 1. So b squared minus 4ac for the numerator is 3 squared minus 4 times 1 times negative 1, which is 9 plus 4. And because this is not a perfect square, it cannot be factored. All right, let's write f of x minus g of x. We are going to write the same fractions, but a negative in between. And I'm going to erase my work. Same LCD. Same numerators, except this is negative. So I want to show you my way that I would use a big fraction bar. I would put x plus 2 times x minus 1 as a common denominator. 1 times x minus 1 minus x times x plus 2. In other words, this doesn't change. This changes to, with a negative sign, to minus x squared minus 2x. So this is x minus 1. So let's write everything at top of it. So this is x minus 1 minus x squared minus 2. So if I want to put this in descending order, minus x squared is the first term, and then x with negative 2x results in minus x, and negative 1 remains. Fg, we multiply the two fractions, 1 over x plus 2 and x over x minus 1. You know, when we multiply fractions, we multiply the tops and the bottom. So the top is x, the bottom is x plus 2 times x minus 1. You can keep it as a product, everybody. Okay, you can keep it as a product, or you can distribute, and if you distribute, let me just write that. If you distribute, you get x squared. 2 minus 1 is plus x. And then 2 times negative 1 is minus 2. You don't have to do that. Finally, we want to divide f of x by g of x. So 1 over x plus 2 over x. And by the way, it's important to write what x cannot be. Clearly, This one or this one says x can't be -2. This one says x can't be 1. So let's write the ratio of f of x to g of x. It's a complex fraction. And because there is precisely one fraction at top, one fraction at the bottom, I'm going to remind you of this. You multiply these two, which is called the extremes. You put them at top. You multiply the two, which is called the means. You put it at the bottom. So the top is x minus 1. The bottom is x times x plus 2. And again, when we go back to the original ones, the two functions, x couldn't be -2, x couldn't be +1. In addition to that, x cannot be 0 either. So we still have the same situation as here, or if you look at those two, and the final result indicates that x can't be 0 either. So you want to be careful with that. Composite functions. Composite functions f of g of x. In the real world, functions frequently occur in which some quantity depends on a variable that in turn depends on another variable. Functions like this are called composite functions, everybody. So functions like this are called composite functions. F of g of x is f of g of x. We've seen this stuff before, of course, in previous courses. Substitute g of x for x in f of x to get f of g of x. G of f of x equals g of f of x. Substitute f of x for x in g of x to get f of g of x. So in short, x belongs to g of x. G of x belongs to f of x. In other words, x is the domain for g of x. G of x becomes the domain for f of x, and we get f or g of x. Composite functions, f of g of x is f of g of x, g of x is equals g of f of x. And by the way, in general, they are not the same. So here's a represented with numbers 1, 3, 7. Here's the function g of x that takes it to the next one. G of x is 3x plus 1. And this one, the f function, takes it to the next one, which has the equation half of x minus 3. If we were to move from here to here directly, what function do we need? So one more time, the g function moves it from here to here. The f function moves it from here to here. If we wanted to do it in one shot, the function is called h of x, which is f of g of x, which is the composite function. So f of a g of x, that means f of 3x plus 1. F has this equation, half of x minus 3, replace the x with whatever g is. So half of x is replaced with 3x plus 1. Clearly, this is 3 halves. Let's just write this. So we get 3 halves x plus 1 half and -3. They add up to -5 halves. Okay, everyone. So that's actually pretty straightforward. Therefore, h of x is 3 halves x minus 5 halves. Just a simple example. If you plug in 1 here, you get 3 halves minus 5 halves, which is minus 2 halves, which is minus 1. If you plug in 3, you get 9 halves minus 5 halves, which is 4 halves or 2. So that's, in essence, we do this in one shot instead of two shots. The function h is the composition of f and g and is denoted FOG, read the composition of f and g, f composed with g, or f circle g. So composition function. Here's the function f of x, 3x plus 8, g of x is 2x minus 5, and we want to find the following, starting with FOG of 3. FOG of 3 by definition is f of g of 3, which means first we have to find g of 3. So we are going to replace the x with 3 here. So g of 3 is 2 times 3. 6 minus 5 is 1. And FOG of 3 now is f of 1. So we use f of x and replace the x with 1, 3 and 8, 11. G of f of 3. That means g of f of 3. So first let's find f evaluated at 3. So if I put the 3 here, I get 3 times 3, 9 and 8, 17. And so g of f of 3 is g of 17. And now g of 17, I'm going to put it into the g function. 2 times 17 minus 5. 2 times 17 is 34. Minus 5 makes it 29. FOG of x. That means f of g of x. That means f of 2x minus 5. That means into the f function, replace the x with 2x minus 5. So what do we get? 6x minus 15 plus 8. These two add up to minus 7. Now, what I want to show you here quickly is if I go back to part A, everybody, where the question was to find FOG of 3. And I found that. Instead, if I found FOG of x, which is 6x minus 7, now I can put the 3 here. 6 times 3, 18 minus 7. I get to the same answer. G of f of x, that means g of f of x. G of f of x, that means g of 3x plus 8. That means that now replace this x with f. So 2 times 3x plus 8 minus 5. Distribute, you get 6x plus 16. 16 with negative 5, they add up to 11. Now going back to part B, I want g of f of 3. If I put the 3 here, because this is g of f of x, I get 18 and 11, 29. So that's another way of finding the first two. Develop C and D and then plug in. F of x is 4x and g of x is x squared plus 2. Find f of g of x and g of f of x. So f of g by definition is f of g of x, which makes it f of x squared plus 2. So into the x of the f function goes x squared plus 2. So 4 times x squared plus 2. Distribute, you get 4x squared plus 8, and you're done. G of f of x is g of f of x or g of 4x. So that means replace the x in the g function with the f function, which is 4x. Therefore, we have 4x quantity squared plus 2. This is 16x squared plus 2. And in general, f of g and g of f, of course, are not equal. They are equal when they are inverse functions. Algebra functions and their domains. Two functions f and g can be combined to form a new function, f plus g, f minus g, fg, and f over g, in a manner similar to the way we add, subtract, multiply, and divide real numbers. So that's pretty straightforward so far. The sum function is f plus g of x. That means f of x plus g of x. The difference function f minus g of x is f of x minus g of x. The product function f g of x is f of x times g of x. And the quotient function f over g of x is f of x over g of x. So nothing brand new. We knew that. The domain of f is A and the domain of g is B. So we are giving them names. The domain of all of these functions, if A intersection B, whatever is in common between the two, because both f of x and g of x have to be defined. Because we can't divide by 0, the domain of this last one, the quotient function, f over g, is therefore x is an element of A intersection B such that g of x is not 0. So all of them A intersection B. For the last one, we have one more restriction. That means the denominator can't be 0. This is red, again, just reminding you. This, which looks like an epsilon red, an element of in set theory, okay? This is the intersection symbol. You remember that? And this is red such that this line segment, such that. So let me read that one more time. The set, the braces represent the set. X, which is an element of A intersection B such that g of x can't be 0. Okay? So all of them, in short, have the same domain, which is A intersection B. This one, the same thing, and the denominator can't be 0. So, example 10, find the domain of f of x equals square root of x and g of x equals square root of 2 minus x. So, as you recall, when you're dealing with the root function, if the index is odd, you have no restrictions, and the answer is all real numbers. When it's even, remember in this case, when we don't write the index is 2, so x greater than or equal to 0, which makes it 0 to infinity, and we can replace it as a set A. For g of x, the same thing. On the radical, the radicand must be positive, 2 minus x greater than or equal to 0. Minus x greater than or equal to minus 2. So x, we're going to divide both sides or multiply both sides by -1, less than or equal to positive 2. So this is from negative infinity to 2, and we call it set B. So B is from negative infinity to 2. Now, we know that f plus g of x is square root of x plus square root of 2 minus x. So what would be the domain for part C? Would be the intersection of these two. what is the intersection of A and B? A intersection B. What is in common between the two? This goes from 0 to infinity. This goes from negative infinity to 2. And I hope you see that. Maybe I write it. It makes it easier to see. So A is from 0 to infinity. B from negative infinity to 2. And if you go with the graph, it makes it easier to see that it's from 0 to 2 included. So let me just quickly show you something on the graph that may make it a tad easier to understand. So for the first one, 0 is included and everything to the right. The second one, okay, first of all, this is a bracket. This is 1, this is 2, this is 3, and let me use a different color, let's say blue. So 2, and again, we have a solid point, everything to left. So what is in common between the two? It's in common from here to here, from 0 to 2. What about FOG? Remember, for F over G, F over G of X, so square root of X over square root of 2 minus X. Basically the same thing, the intersection. The only thing is the denominator can't be 0, right? So it's the same as A intersection with G of X can't be 0. What makes the denominator 0 when X is a 2? So let me write that. So the denominator becomes 0 if X is 2, so 2 must be excluded. So we have the same thing, bracket 0 comma 2, but the bracket on the side of 2 changes to parentheses because 2 is not included. Composite functions and their domains. Suppose that y equals f of u or square root of u and u equals g of x or x squared plus 1. Y equals f of u equals f of g of x, which makes it f of x squared plus 1, which makes it square root of x squared plus 1. X is the input, the domain for g. G of x becomes the input or the domain for f. F of g of x becomes the output. So x that's a function machine, okay? X goes to g, g goes to f, results in f of g. Composite function f of g of x is f of g of x. And now the domain of f of g is the set of all x in the domain of g, such that g of x is in the domain of f. In other words, f of g of x is defined whenever both g and f of g of x are defined. Okay, so g of x must be defined, so any x not in the domain of g must be excluded. F of g of x must be defined, so any x for which g of x is not in the domain of f must be excluded. Meaning what? If I'm interested in finding the composite function, I go through the process and I find f of g of x. If I'm interested in finding the domain, Number one, the restriction comes from g of x, the domain within the domain. Okay, g of x must be defined. So anything that is excluded from g of x is out. In other words, first find the domain of g of x, and then look at f of g of x. Anything in f of g of x that must be excluded, you make a note of it and you exclude it from the domain of g of x. So the restriction in essence is, what is the shortest version of this concept and the easiest version of this concept? What is the domain of f of g of x? Whatever is the domain of g of x minus whatever makes f of g undefined. So x with the g function takes you to g of x. This portion of x takes you to g of x, this portion. This is the domain of f. It takes you to f of g of x. Domain of f of g is the portion that is taking you from g to f of g without any restrictions and problems. Again, a quick recap. Find the domain of g of x. Exclude anything that you must from the resulting function. So here's a simple example. Find the composite function. First, f of x is x squared. G of x equals x minus 3. And we want to find f of g as well as g of f. So f of g is f of g of x, which means replace the x with x minus 3, and you get x minus 3 squared. What about g of f? Is g of f of x. And that means g of x squared, which makes it x squared minus 3. Now, f of x is square root of x minus 3. G of x equals x squared. H of x is x cubed plus 6. Find f of g o h. First, let's find f of g. F of g or f of g of x. So we are going to replace the x with x squared. So f of g or f of g of x simply becomes the square root of x squared minus 3. Okay. Now, f of g o h. F of g o h. So into this function, f of g goes h. Replace the x with whatever this expression is. So it becomes the square root of parentheses x cubed plus 6 squared minus 3. So this will replace the x just by definition of a composite function, everybody. Express the function capital F of x equals square root of x plus 2 over square root of x in the form of f of g. Find f of x and g of x. So this is f of g. That's what they're asking. So it's by inspection, and there may be different ways of approaching them. Notice over here you have square root of x plus 2 over square root of x. If the f function represents x plus 2 over x, and g of x is square root of x, it will do the job. So one more time, f of x is x plus 2 over x, and g of x square root of x over x. Normally, this is by inspection, everybody, and it's not unique. Use the given graphs of f and g to evaluate each expression, or if the expression is undefined, enter undefined. The f function, the g function. So we have the red one as the f function, the blue one as a g function. We want f of g of 2, which means we are going to find g of 2 first. So g is the blue one. So you are going to locate 2 along the x-axis. On the function g of x, the blue one, you locate its y coordinate 1, 2, 3, 4, 5. So g of 2 is 5. Therefore, you want f of g of 2 or f of 5. So you locate 5, 1, 2, 3, 4, 5 along the x-axis. And it gives you this point, which has the y coordinate 4. G of f of 0. So first and foremost, we need f of 0. Again, f is the blue one. F of 0. So locate the 0 along the x-axis. This point has coordinates 0, 0. So f of 0 is 0. So you want g of 0. Now g of 0 has the y coordinate 3. And you're done. F or g of 0. That means f of g of 0. Which is f of 3 because we already have g of 0. Remember that? So f of 3. So along the x-axis, locate the 3. 1, 2, 3. Well, it's just the red function. So it's simply this point 0. The answer is 0. G or f of 6. It means g of f of 6. So 1, 2, 3, 4, 5, 6 is this point. So it's g of 6. And as you look at the blue function, it stops here at 1, 2, 3, 4. We don't have any more. So it's equal to g of 6, but this value is not defined because there is no point on the graph of g that has x coordinate 6. So we don't know, it's undefined. GOG of negative 2, that means G of negative 2. That's the meaning of it. So let's find G of negative 2. So 1 and 2 on the left gives us negative 2. And this is the point having a y coordinate 1. So G of negative 2 is G of 1. And 1, this is 1, 2, 3, 4. It's G of 1. And the answer is 4. F of 4, that means find f of 4. So first let's find f of 4. So 1, 2, 3, 4. And the function f is the red one. It's this point. Okay, that was early. I didn't. Okay, first this one. I have that point, which results in 2. Okay, so f of 4 or f of a 2. Now f of 2, 1, 2 results in this point, which has a y coordinate negative 2. This is how you evaluate composite function on a graph of a function.